That's right. Good morning. This is the second part of the uh, Epidemiology in Clinical Practice series. And in the first part, I had talked about how to actually interpret research data. And in this part, the outline of this session is I shall start with trying to help you how to use research evidence to inform your clinical decisions. Let's start with using evidence from a single study, and then how do you use evidence from a body of studies? Many studies are there. And this will bring us into explaining to people what systematic reviews and meta-analysis are. Okay, good morning. I'm Prathap, and what I'm planning to do in this session is to help you to understand the ways in which you can use epidemiology in clinical practice. And this is part 2 of the series. So in the last part, I had explained how we can interpret clinical evidence or whatever evidence you have to see how applicable and how useful it is to you in your clinical practice. And in this session, what I hope to do is to help you to figure out how to use this evidence from research to make a clinical decision. And we'll start with trying to use it from a single study, and then we will move to try and see how we can use evidence from a number of studies, a body of evidence. And that will bring us into what we call systematic reviews and meta-analysis. And I'll spend some time explaining to you what these are and how they're useful. And also finally tell you how can you be sure, how confident are you that the results of all these studies are likely to be true and useful outside the research setting and in your clinical practice. And it'll also tell us how people use this kind of evidence to make a policy decision, like in terms of a guideline or a policy that a nation might make. So that's what I hope to cover in this session of the series. Now, all of this relates to the whole concept of evidence-based medicine, which was a term coined by Gordon Guyatt from McMaster University in Canada, who along with Dave Sackett, they defined evidence-based medicine as the integration of research evidence, clinical expertise, and the values of the patients that we are treating. So this integrated approach is meant to be an alliance between good clinical evidence or evidence about prognosis or diagnosis or treatment that an astute clinician would use to make a decision about patients. Now, the problem is over the years, we've kind of figured out that evidence-based medicine, that term, probably is a myth because it kind of assumes that there will be evidence. And that's not always true. It also assumes that that evidence is enough to make a clinical decision, which I'll demonstrate to you is not always true. And it also assumes that the evidence indicates that whatever intervention it's talking about will be available, it will be affordable, it will be applicable, and it will be preferable. So because of these problems, we prefer to use the word evidence-informed healthcare. This acknowledges that reliable evidence may not exist, but at least you need to know what is the evidence and how reliable it is. And it acknowledges that even if the evidence is good, it has to be contextualized for your local use. So we have to look at the balance of benefits and harms, costs, preferences, or if there are other alternatives. So in this paradigm, evidence only informs your decision. It is not the decision. You make the decision based on the evidence and the contextualization of that evidence. So that way, if you look at it, it's a two-stage process where you first need to get reliable evidence from what is published as research, which is relevant to your need. This you do by synthesizing the evidence from all the studies addressing those questions. Then you make the decision about should I use the evidence, which is how you contextualize it. And these two are clear processes which we will discuss today. So I don't know whether you remember my friend that I talked about in my last session, part 1, And this was a problem that a friend of mine from my childhood gave to me regarding her condition. She was an employed woman, a journalist in the last trimester of her second pregnancy, who had a prior neonatal death because the neonate was born with respiratory distress syndrome. And she was pregnant again, and she's a high-risk pregnancy. And her doctor advised her to try a short course of corticosteroids to prevent neonatal death. She was not very sure whether it will help or whether it would harm, and looked to me and my colleagues in CMC to see if we can find some way of guiding her based on some evidence. And remember, I had mentioned last time that I couldn't find this information from talking to my consultant friends, so I decided to look for the evidence myself. And when I wanted to look for it in PubMed, I realized I need to rephrase this question in an answerable manner. So I reframed it as, in mothers at high risk of premature delivery, will a short course of corticosteroids compared to no steroids prevent or reduce neonatal deaths? So what I had to do was define the population, the intervention, the comparison, and the outcome. And the time point here was in the neonatal period. And the study design I felt would best answer this question without bias was a randomized controlled trial. And I looked in PubMed and I found this trial by Liggins, published in Pediatrics 1972, where mothers due to deliver preterm were given steroids and no steroids, and the outcome was neonatal death. And the numbers here are 532 mothers randomized to steroids and 36 neonates died. 538 mothers randomized not to get steroids and 16 neonates died. And the important thing for us is to see how important this difference is. So I found out that steroids are clearly better than no steroids because risk ratio was 0.61 and the confidence interval was 0.41 to 0.9, which basically means the risk reduction, 1 minus risk ratio, showed that steroids would reduce the risk of neonatal death by 39%. That is, 1 minus 0.61 is 39. So it can be expressed as a percentage, or you can even say 100 minus 61. 39% reduced risk of dying for the neonate if steroids are taken by the mother compared to not taking steroids. And the confidence interval is from 59% reduction to at least a 10% reduction in the risk of dying. Another way of looking at it is how many neonates would be prevented from dying. This is the risk difference, which is one risk in one group minus the risk in the other group. And it's 0.044. So if you look at it in terms of number of deaths prevented per 100 neonates born, then it will be 0.044 divided by 100 and rounded off. So this will show that steroids will prevent 4 fewer neonatal deaths per 100 births compared to no steroids, which from the confidence interval ranges from 1 fewer to 8 fewer deaths. The other way of looking at this was to see how many mothers you'd have to treat with steroids to prevent 1 neonate dying. And the number needed to treat here showed, for benefit, you'd need to treat 23 mothers with steroids to prevent 1 neonatal death compared to no steroids, from 12 to 104 mothers. Now, we could use either of these statistics, but patients somehow tend to understand relative risks better. So we now have the decision to make. What do we tell my friend? So before that, we also had to make sure that the study had no biases. And so we looked to see whether Liggins, in 1972, had any selection bias or performance bias or detection bias or attrition bias or reporting biases. And we found that this study was well done. There were no methodological problems. So these are the actual results. Now we move to this presentation where we have to make the decision. How do we decide whether my friend should use steroids? I'm not talking about generalizing it to anybody, but to my friend. So we've discussed and shown you that steroids are effective clinically, and also there's not a chance difference. The outcome is very important for my friend because it's a precious baby. And we also know that the methods of the study were good, so we can trust the results. So this we have decided in the last session itself. Now our question is, what are the other questions we need to ask before we can say my friend should use steroids? If any of you have an idea of what are the other questions we might need to know, I'd be happy to, respond to that. So we know that if you use steroids, you reduce the risk of death by 39%, at the very least a 10% reduction in death. And this is a very important outcome for my friend. And we know the study was done well, so those results can be trusted. They're likely to be true results. What would be the other questions as clinicians we would like to know before we can advise my friend that, yes, go ahead and use steroids? Anybody? Okay, so one of the questions people might ask is, how do you know that results from a study done in women from New Zealand are going to work for people in India, for women in India? So that's a common question. So how do you realize, how can you extrapolate from a study done somewhere else? So the two things to keep in mind are there could be a biological reason why women in India will not respond as well as women in New Zealand. I could not think of any biological reason why women in India will not have the same response with steroids as women in New Zealand. I don't know of any. So I didn't think that was an issue. But there could be other issues in terms of health systems delivery. That the systems where the childbirth takes place in New Zealand could be different from the health systems in India, and that might matter, especially in terms of adverse events. Now, the paper itself did not report any serious adverse events or any major issues with steroids in the Liggins trial, but keep in mind it was done in a high-income country in a good hospital setup. So the question was, if it was not done in a high-income country in a good hospital setup, would there be a problem? So infection was one of the issues that was a concern. But if the study showed that if you deliver in a good hygienic circumstances, there's no increase in risk of infection. And I was also fairly sure that my friend would deliver under good hygienic circumstances because she's reasonably well-to-do. And she was interested enough in this problem to actually ask me for evidence. So I didn't think that was a major issue. The only other adverse event I could think of was maybe she'd get some gastritis, but that is not a major problem. You can always treat it. So the benefits outweighed the risks. So that question, that tick box was checked. The next problem could be, is it affordable? Now we all know that steroids are relatively cheap. So that's not a problem. The next question is it available? Steroids are available across the counter without even a prescription. So that's not a problem. The next question we have to ask is it practical to take? For example, do we have to get admitted? Is it a difficult procedure? There are no barriers to taking steroids because it's just a simple pill you take. So that was also not a problem. Next question was, are there any other alternatives? Well, at that point in time, I couldn't think of any other alternatives, and that seemed like the safest and the most efficient alternative. The next question was, what is the preference of my friend? Now, you cannot ask my friend, I cannot ask my friend, what is your preference, unless I give her information about all the other bits that we had just discussed. So in a way, this is exactly what we do in clinical practice. And I'm just articulating it to you. This is what we should be doing. And we know that something works. We, in our minds, go through these processes before we advise our patients or discuss with our patients and make a shared decision. Now, are there any other questions you might think is important here? Or do we think we've got all the questions and we can now tell my friend, please use steroids? Can I ask you guys, how many of you would say, yes, let's tell my friend to use steroids? Just type in yes. Or how many of you think we should be no? Okay, probably you don't know what we should be doing. The next question we should be asking is, how do you know that we have all the evidence? Because we only have one trial. So this is the problem in the real world, that evidence from one trial is really not enough to be sure that something really will work. And I'm now giving you the results in a graphical manner. So what you have here is a vertical line, which represents the line of no difference. The relative risk is 1. To the left of the line is less than 1. So you have 0.5, 0.2. And to the right of the line, you have more than 1. It is a relative risk of 2 and 5. Okay, Now, what I have here, I'm graphically representing the results from Liggins 1972, where 0.61 is a black blob in the center, 0.41 is the extreme left, and 0.9 is the end which is closest to 1. So one look at that and you know that anything less than 1 favors the experimental intervention, which is steroids here. And from the width of the confidence interval, you know it does not cross 1. So it clearly shows you that the best estimate and the least estimate of steroids are that it will reduce the risk of death. Okay? So that's a graphical representation of the trial we had. But I also found another study. This was a study with the same echo, same population intervention, control and outcome. But here the sample size was smaller. So the confidence intervals were wider and also included the possibility of a relative risk of 2.24, although the estimate was 0.82, reduces the risk of death by 18%, and the best estimate was 0.30, reduces the risk of death by 70%. Here, it also suggested there could be an increase in the risk of death by 124%, if there is a word like 124%. But it shows that there was at least a doubling of the risk, could be a doubling of the risk. So this is the kind of situation you get where one trial tells you something works and the other tells you it doesn't work. So it is around this time that I came across the logo of an organization called the Cochrane Collaboration. And in the center are shown the results of 7 trials from a systematic review of steroids versus no steroids to prevent death due to preterm births. And because they were systematic in their search, they found more trials than I had. And 2 of those trials favored steroids, one of which was Liggins, the one on the top. But they also found 5 other trials which showed no significant difference. One of them is a trial that we suggested that it might even harm. So now we have a problem. We've got 5 trials showing that it might not help or it might harm, and 2 saying it will help. How do you make a decision with that? So very often, people use what is called the vote counting approach. It will count votes. Which intervention has, which outcome has more votes, the 5 or the 2? The problem with this kind of, way of looking at it is, the 2 trials are large trials, which had a lot of events and very narrow confidence intervals. The 5 trials are smaller trials, but one large trial and one small trial cancel each other out. That doesn't really make sense. So this vote counting is not as good as what happened here, which is called a meta-analysis, where instead of counting votes, they're pooling the relative risk and confidence intervals of all the studies and giving more weight to the studies which had narrow confidence intervals, right? And that pooled effect estimate is represented by this diamond at the bottom. And that diamond does not cross over into no difference. It clearly tells you that steroids save lives. So I had no hesitation in telling my friend that the evidence from these studies suggests that steroids reduces the risk of death by so much, and at the very least, it will reduce the risk of death by this much. And we really don't have many other alternatives, and there don't seem to be any risks in taking it, unless, particularly if you deliver in hygienic circumstances. And it's a relatively cheap intervention, and let's give it a shot. So this is how, in clinical practice, you can use evidence from a systematic review of randomized trials to be, of use in informing our patients about what the research evidence is. I want you now to ask myself, did we make the right decision then? It was a long time ago, 1995. So I looked at the more recent update. There's even an update after this. But this particular update had found 21 studies. That's because Cochrane reviews keep getting updated every time some new evidence comes out. So in these 21 studies, there are a larger number of women, and they clearly showed that treatment with antenatal corticosteroids does not increase risk of death to the mother, chorioamnitis, or puerperal sepsis. But the point is, most of these studies were done in high-income countries in hygienic circumstances. But people have shown that when you start upscaling this intervention to low-income countries, and the hygienic circumstances are not very good, there is an increased risk of neonatal sepsis. So whatever these results are pertain to the studies that were included in the meta-analysis. And they didn't really have any trials because there weren't any trials from low and middle income countries. But observational evidence, when this evidence is being used in low and middle income countries, suggests that you should be careful that neonatal sepsis is not a problem. But what this review confirmed, was from 18 studies that neonatal death is reduced. And you're more confident of this because your confidence intervals are now 0.58 to 0.81. They're more narrow, right? Not very different from ligands, but ligands is a very large study and probably contributed a lot of weight to the overall result estimate. Now, this systematic review also gave us many more results about RDS, about cerebroventricular hemorrhage, about necrotizing enterocolitis, about respiratory support, intensive care admissions, systemic infections. So what happens is that one trial will have a few outcomes. When you do a systematic review and you have many trials, many of them have other outcomes. And therefore, you now have a whole body of evidence of this comparison with a whole lot of outcomes that a single trial may not be able to study. So that's one important lesson we learn from looking at systematic reviews, that you get more information from just looking at one trial. And because the sample sizes are now, the pooled sample sizes are large, you get more precision in your effect estimate. Now I want you to learn one quick trick. I want you to be able to look at these outcomes and the results and say which of these outcomes are statistically significant and likely to be clinically important. Okay, let's take the first one, RDS. So the relative risk is 0.66. Now the first question we ask ourselves is respiratory distress syndrome a desirable or an undesirable outcome? Now you'll agree that it's an undesirable outcome. We don't want it. So for any undesirable outcome, a relative risk less than 1, like this is 0.6 is, it suggests that the experimental intervention, which is in this case steroids, is better than the control, which is placebo, right? The steroids are better than placebo. That's the first thing we learned from RR of 0.66. The next thing we want to know is how much better. So you can do 100 minus 66. That gives you a 34% risk reduction, relative risk reduction of steroids versus no steroids. Steroids reduces the risk of death by respiratory distress syndrome by 34%. And the confidence interval tells you what is the best estimate and what is the least estimate. The best estimate is 0.59, which is 100 minus 59, which is about 41%. Yeah, 41% reduction. And the least estimate is 0.73. So what it says, at the very least, you expect a risk reduction for RDS of 27%. Now, 27% is a pretty good reduction. The least estimate, or what we call the minimum expected difference, right, is 27% reduction in the risk of respiratory distress syndrome. So here we think that because it doesn't cross 1, it is statistically significant. And because a minimum estimate of a 27% reduction in the risk of death is pretty good, it's clinically very useful, right? So this result is both clinically as well as statistically important. The next one, cerebroventricular hemorrhage, 0.54 is a good risk reduction, and the least estimate is 0.69, which is a 31% reduction in the risk of cerebroventricular hemorrhage. That is clinically important, and statistically this is significant. Necrotizing enterocolitis, the relative risk is 0.46, and the least estimate is 0.74, which is a 26% reduction in the risk of developing necrotizing enterocolitis. Now this is also very useful. Now what I'm trying to say here is these risk estimates and their confidence intervals come from randomized controlled studies where you control everything, right? So when you actually use it in the real world where you don't control anything, your results are not going to be so good. So if you start off with the least estimate of benefit of at least a 25% reduction, you can be fairly sure that in the real world you will get some benefit. But if you start out with a very low, least estimate, very minimal, then you're not very sure it will translate into any clear benefit in the real world, which is what happens in the next example of respiratory support and intensive care admissions, where your relative risk is 0.8. Now, a 0.8 relative risk is a risk reduction of 20%, which itself is not very good. Then when you look at the least estimate is 0.99, which is a 1% difference in the risk of respiratory support and intensive care admission between steroids and placebo. So because the confidence interval don't include one, they don't cross over to the other side, you'll say this is statistically significant. But a least estimate of 1%, they're not very sure it's going to be clinically important. That's largely because the data comes only from 2 studies with only 277 infants. So we're not sure. Although statistically it says this is not due to chance, clinically we're not very sure that the minimum we want, even from the risk estimate, is good enough to be sure that when we translate it in the real world, we'll get some benefit. The next one is systemic infections in the first 48 hours of life. And your least estimate here is 0.85, which is a 15% reduction in systemic infections. Now, if it was, say, if it was 0.75 or 74, 25% or more, then you can be reasonably sure that's a good minimum difference. 0.85 could also be good, depending on the outcome. If you feel that a 15% reduction in systemic infections in the first 48 hours of life is important, then that's good. So as you can see, they've moved away from just looking at p-values to tell us how useful an intervention is to starting to look at relative risks and confidence intervals. So now we are also saying it's not just enough that the confidence intervals do not include one. Statistical significance is not enough. We want to know what is the least estimate of benefit from your confidence interval, because that will give us an idea that is it really a robust result because it shows a good clinical benefit, or is it only a marginal clinical benefit? So that's one thing we need to keep in mind anytime you look at relative risk and confidence intervals. You have to ask yourself, what is the estimate? Is that estimate of effect likely to be clinically useful? And what is the least estimate? And where you keep your minimum important difference for the least estimate depends on the outcome. Because if the outcome is death, even a 5% difference reduction may be useful, because if it's a public health intervention and you are treating a lot of people who might die, that will translate into a large number of absolute benefit. So I hope you understand these concepts, okay? Because that's what I'd like to, conclude by saying that in this example, I was able to show you that updated evidence from trials clearly indicates that steroids reduce the risk of neonatal death without major adverse events for the mother. So that was the best advice I could find for my friend. And it also told me that systematic reviews provide answers that individual trials cannot provide. Okay, so what we have now addressed is the issue of finding the right evidence. And we found this through a systematic review and meta-analysis. The next step would be the process where people make the decision for using this systematic review, using the results. And I showed you from a clinical perspective, how do we go about doing that? From a single trial and from multiple trials. Okay? And there are software which organizations like Cochrane use to develop this grade process and the summary of findings, which I'll talk about a little later on in this presentation. So since systematic reviews are considered to be kind of like a gold standard for any question, whether it's interventions or diagnosis or prognosis, we look to see what is the best primary design for that question, and a systematic review of studies following that primary design, like in this case RCTs, ideally should be the best evidence that is available for you. So a systematic review is not like a review article. It is a scientific strategy that tries to limit bias in the way you ask the question you frame your entire search strategy and what studies you'd include and what you'd exclude, and how you assess each study for how well it was done and whether there was any biases, and how you extract the data for each of the outcomes and what the important outcomes are. So it's kind of a study of other studies. So it's called, in some ways, it's called secondary research, but in some ways, it's also primary research because you're framing the question like you want to do in the study, but your population is not people, but it is studies done on people. And if you find that the studies that you retrieve are all very similar in the questions they're asking and the way they've addressed the whole study, then you can pool the results using meta-analysis. But sometimes you will find that the studies are all quite different in the way they've approached, the way they frame the question, the populations are different, or the outcomes are different, or the way they have measured the outcomes are different. Then you might decide, I will not pool the results, I will not do a meta-analysis, and I'll report my results narratively. And we really use systematic reviews, but individual trials cannot answer all the questions we may have in mind. Now, meta-analysis per se is only one optional part of a systematic review, right? It just refers to the statistical technique of combining the numerical results of the individual studies. And what it attempts to do is to say, across all these studies, on average, how does drug A compare to drug B for the outcome of death or for relapse or any other outcome? What is the average result across the trials? So you can use this method of averaging the results of meta-analysis for studies which have evaluated prevalence, incidence, diagnosis, prognosis, and the effects of the interventions. The major advantage is because when you pool the results of the studies, right, you get more power. Your sample size increases tremendously, and that can help you to get more precision, which the individual studies could not give you because they were smaller. So this pooling all the results of the studies to see what is the average effect across the studies is what meta-analysis tries to do. Now the problem is, if you do a meta-analysis of easily available studies and not go in for a systematic search for all the studies and use the protocol of a systematic review, you might get wrong results. And there are three major reasons why this can happen. Suppose I just take 5 studies that I have with me and pool the results of all the studies. I will get a result. But what I must ask myself is, how did I get those studies? See, one of the things that you must keep in mind is that studies that are easily retrieved are more likely to be reported in English, more likely to have positive results, and more likely to be indexed in PubMed. This is because there's something called publication bias, where people who have got positive results from their studies are more eager to publish the results. Journal editors are more likely to accept a positive result for publication, and you're also more likely to have it. You find studies which are indexed in PubMed, which generally favors English language studies. So you forget that there are many studies which are not in English and are indexed in other databases apart from PubMed. Because PubMed is Medline is largely North American focused. There is another database called Embase, which is where many of the Europeans publish their studies. And the overlap between PubMed and Embase is not very great. And then there's the Chinese language registers, and including in India, there are many journals which publish trials. The journals are not indexed in any of these databases. So you might miss all those studies. And then there are negative studies which may be published, or at least presented in a conference, but not necessarily published. So the point here is, if you just take easily available studies and pool their results, considering that they're more likely to be positive results, you will get positive results. Unless you can get all the studies and pool their results, you will not get a balanced answer. So that's one reason why doing a meta-analysis outside a systematic review can give you wrong results. You need to have a systematic search strategy. Second important thing is, it's not just important to just pool the numbers. You will get a result. But you must keep in mind that those results from the studies come from trials where the methods matter. If the risk of bias in one study was pretty high, then the result of that study cannot be trusted. So if many of the studies in your meta-analysis have poor methods, then your final result cannot be trusted. So you need to have a strategy in your review which says that this is the method by which I'm going to look at the individual risks in the studies and then look to see in the pooled result of all these studies, how many of these studies were badly done and likely to be flawed in their results. So that's the other process, the systematic reviews, plan and do. And the third thing to keep in mind is it's not just enough to just pool the results and say, this is my overall result. Remember, we are saying this is the average result across the studies. Now, but if the studies themselves are showing very widely differing results, you can get an average, it'll be like a median. But that doesn't necessarily tell you why these outliers are there. So unless we can understand the reasons why some of these studies may not show consistent results with your pooled estimate, then you're really not making a wise decision. So the three things that we need to do in a systematic review, which will help the meta-analysis, is to make sure, first of all, that your question is a valid question, then that you really searched and found all the studies done on that comparative topic, and that you found a good valid method of evaluating the risk of bias in all these studies, and then seeing how much of that bias would influence the pooled results of the studies. And then we also need to see that the pooled result is a consistent result in all the studies, or if it's inconsistent, that we can understand why it is inconsistent. What are the reasons why in some studies the drug works better than in other studies? That's what meta-analysis ideally should be. So many of you have obviously read review articles. Now there's a big difference between a review article that you read and a systematic review, particularly a Cochrane review. And the main thing is that a review article is written to provide an up-to-date, state of the art of what's going on. And it may have very broad objectives. A systematic review, particularly Cochrane reviews, are very focused. And they're only done if they think that the particular question has got some clinical application in either answering a controversy or giving you confirmatory evidence that this is a good or a bad intervention. So it always addresses a focused clinical question in the form of a PICO, population intervention comparison outcome and time points. The major difference between a review article and a Cochrane review or systematic review is review articles don't have a method section. They don't have a section saying this is what we did, how we did it, why we did it, nothing. The person does it. And you cannot reproduce it because you do not know why he did what he did. Whereas in the systematic review, particularly Cochrane review, the protocol is peer-reviewed and published with reviewers' comments before you start doing the actual review. So it's very transparent. We're telling you in advance, this is what we aim to do and these are our methods. You can also do a non-Cochrane systematic review, in which case you're expected to, or rather encouraged to, register the key elements of your protocol in a website called Prospero. So this is a prospective registration of systematic reviews and stuff. And that will give you a Prospero registration number, just like a clinical trials registration number. And that will significantly enhance your chances of getting a systematic review, non-Cochrane systematic review published in a good journal. So this method of, restating what your objectives and methods are will help people who are reading these reviews to see, did you change your results section based on what you found, what your data was? Or did you stick to your original plan and report your results as you intended to? So to prevent fiddling around with your results. Another difference is that systematic reviews, particularly Cochrane reviews, never have only one author. You have a mix of authors with different levels of expertise in the topic and method section. And often you may find good systematic reviews include patient groups or patient representatives to give a perspective from all points of view, not just a clinician's point of view or a researcher's point of view. And one of the things that systematic reviews try to do is to ensure that conflicts of interest, whether it's academic or whether it's financial, are declared. And Cochrane reviews do not allow any commercial conflicts of interest to influence the reviews, and they do their best to try and identify academic conflicts of interest. For example, if one of the people had done a trial and then he wants to do a systematic review, we have to be careful that that person may be biased towards the results of the systematic. The other important difference is that there are no real standards for how you write a review article, but there are very clear reporting standards for Cochrane systematic reviews like PRISMA. And other differences are that, in a Cochrane review, the protocol is very, very detailed. It tells you this is the kind of studies we're looking for, these are the kind of studies we will exclude. And when you actually find the studies, whichever studies you exclude, you will say these are the studies we exclude and the reasons why we excluded them. And the search strategy in a systematic review is pretty extensive. In the whole section of what databases we propose to search and what are the search strategies we use, and they don't restrict it by language. And we also, so it's a very detailed search strategy. You won't find anything like that in a narrative, in a traditional review article. And when you select the studies, that's described. This is how we're going to select the studies. These two people will independently select studies. How will they deal with duplicates? And how will we assess risk of bias in each of these studies? What are the criteria we use? And how are we going to pool the results of the study? So the protocol itself is really, really important, because if you get the protocol right, then the systematic review is likely to be valid. And when we pool the results, we don't use vote counting, or we don't bother about p-values. We look only at, pooling the relative risks and confidence intervals, and we give different weights when we pool the results. I'll show you how it's done. The other important thing is that every step of the systematic review is done in parallel, independently, to ensure that biases are reduced. And then when you publish your protocol, you make sure that you tell people, okay, this is what changes we've made in the review compared to the protocol, and this is why we did it. So you try and minimize bias in doing the review. And when you interpret the results, it's not your opinion. It's basically based on a summary of findings table for the key outcomes using a grade assessment. I'll describe that to you. What it does is it tells you, okay, this is the result, this is the absolute benefit you get, this is the relative risk, and this is the confidence that we have that you will get these results. I'll show you how you make these confidence assessments. And when we conclude the review, we don't make any recommendations in systematic reviews, because that's the job of people who are going to use it. We can discuss the implications, we can tell you what the implications are of the findings. And Cochrane reviews are regularly updated when you have new evidence. And if you think that there will be no new evidence, they'll say, okay, we are no longer updating this review because we have enough evidence. One of the big things about a Cochrane systematic review is that it's done by a team. Once the Cochrane group feels that this is a good review topic and people who plan to do the review are qualified to do it, they support you right through the whole thing. They will find the trials for you, they'll help you with the publication and also the dissemination. So it works the other way from doing a review article, where if they commission you to do an article, that's fine. But most of the time, you will write the review article and then you'll have to find a journal who wants to publish it. At the bottom line is that there are review articles, traditional review articles, which are very influential. But that depends largely on who wrote it. If that person is influential, the review article becomes influential. In Cochrane reviews, it doesn't matter who wrote it. The fact that it's a Cochrane review is a brand, it's a standard. And that's the importance of how influential they are, because they are very often used in WHO and other guidelines. So that's the difference between these reviews. And this is the reporting standard, the PRISMA statement on how you should report systematic review. You can download this from just typing PRISMA or from the Equator Network website. But I want to now tell you what are the other major problems with traditional review articles. Because traditional review articles, or if you just look at textbooks as a form of a review article, they can mislead you. And this example I'm going to give you is from the NEJM, New England Journal of Medicine, by a guy called Joseph Lau and his colleagues. In 1992, they looked at what you see here is a forest plot, which is basically a forest of lines, but each line represents a trial. And there are 33 trials. These are the odds ratios and confidence intervals of 33 trials. done over 30 years, 1959 to 1988, where they randomized more than 36,000 patients to get IV streptokinase or no IV streptokinase after a myocardial infarction to prevent death. Now, if you look at these odds ratios and whether they cross one or not, they're all over the place. You can't really make up your mind. But when you pool the results, you get a very precise estimate, which basically tells you that steroids definitely, saves lives. The confidence interval is so narrow you can't even see it. It's absorbed in the whole estimate. So we now know very clearly by pooling the results that using, streptokinase saves lives after myocardial infarction. But the authors asked, did it require 30 years and 36,000 patients and 33 trials to come to this conclusion? So what they did on the right is a cumulative meta-analysis, by which what the authors did was they took the first trial and pooled the results of the second trial. So this 23 and 42 patients between 65. That's a cumulative pool total at that point in time. Then they pooled the next trial to this one. So they kept pooling each trial as if they were being pooled by year of publication. And they were able to show that by 1973, after having randomized only 2,432 patients, that the pooled effect estimates and confidence intervals showed you that streptokinase saves lives. But what did the world do? It kept randomizing patients. So in 1986, we had GC1, which randomized 11,712 people. When you had ISIS-2 in 1988, 17,000 odd people were randomized. Now the point is this, what if you were in an ethics committee or an IRB in 1973 and requests for future trials, including GC and ISIS, came up? If you had the pool results, it's very, very unlikely that you would allow any of those trials to take place because it would have been unethical to do so. Half the people in those trials were being randomized to probably die. So in the world of research, we were killing people because we didn't know how to look at cumulative evidence. What were we doing in the real world? Not very different, because what were the textbooks and the reviews recommending? Not streptokinase, not thrombolysis. Even though the research evidence was clear by 1973 or so, it was only in 1985 that you had the first specific recommendation to use streptokinase in any textbook or review article, right? And what were they recommending instead? Potentially harmful interventions as routine. So prophylactic lidocaine after acute MI was being recommended right up to 1989 or so, or even 1990, when the cumulative evidence was clearly showing that lidocaine doesn't help and probably harms. So this is the tragedy. And this was reflected in an editorial by Antman in JAMA. It said advice on some life-saving therapies has been delayed by more than a decade, while other treatments have been recommended long after controlled research has shown them to be harmful. So this led, many people to realize that before you do new research, you've got to look at a systematic review and see what that shows, whether you need more evidence, right? And whether the systematic review has been done properly, and whether meta-analysis was done properly, and what do the results show? How confident are you that this systematic review's results can be trusted and is likely to be true for you? Then you decide whether you need to do a new trial. So there's an organization called Cochrane, which is now trusted for giving you good quality evidence, and it's named after this gentleman called Archie Cochrane, who, when he was the head of the Medical Research Council in the UK in the 50s, he was asked by the government, because they were setting up the National Health Service, and the National Health Service plan was to provide free treatment to all the people in the UK. So the government turned to Archie Cochrane, the head of the MRC, and told him, please tell us which are the treatments that we should fund, which are the ones that work. So that's when he looked around and found there's no place which tells you which are the treatments that work and which don't work. So in one of his books he wrote, it's surely a great criticism of our profession that we don't have in one place a critically organized summary of all the trials that we do, of all the treatments that we give to see whether they work or they don't work. And that's the challenge that this organization called Cochrane has been trying to address for over 20 years, and more than 25 years now since it was formed. And it's the world's largest organization which is devoted to producing, disseminating, and maintaining systematic reviews of the effects of interventions. Now it also does systematic reviews on the accuracy of diagnostic tests. This is largely done by volunteers from more than 130 countries who share the same principle that we need to know what is the truth from all the research evidence. It has a very strong editorial unit and collaborative review groups who help produce these systematic reviews. And they have made available freely for anyone to use proprietary software to do the reviews called Review Manager, and another software which utilizes the results from the review to prepare summary of findings which can be used by policymakers. The main output of the Cochrane collaboration is in the Cochrane Library. And the Cochrane Library has evidence which is considered to be trusted because of the methods used by Cochrane and because of the fact that there is no industry funding. We don't allow, other influences to influence our results. So people consider Cochrane to give you, reliable evidence. The website that will give you information on Cochrane is cochrane.org. It talks about the organization. It also gives you a summary of their reviews. There is one section here which talks about how you can join Cochrane. So it's probably worth going and taking a look at that to see how you can contribute. There are many ways you can contribute. The other website is the main results of this. It's called the Cochrane Library. And you can just write Cochrane Library and you will get this. Now this one is under a paywall, and there are some open access reviews in this, but many of them need to be paid. And we actually have managed to get the ICMR to fund a free subscription for everybody in India till about last year. And now it's under, we're hoping to get this license back again. So Cochrane reviews are sometimes very controversial. They often tell you that the things we do don't offer any benefit, like mammograms only. Evidence suggests it may not really help. And they're very influential because, for example, the oral rehydration solution became a worldwide, standard after a Cochrane review partnered with UNICEF showed the benefits of ORS. Magnesium sulfate is currently considered the drug of choice for eclampsia and preeclampsia. But in the early days, when Cochrane did their first review, they found that the world was using diazepam and valproate and other anti-epileptic drugs. So phenytoin, for example. So they did a trial which showed that MagSulf actually is probably preferential, and that has now become this Cochrane review of these trials has established MagSulf as a standard of care for eclampsia and preeclampsia. And it's not just drugs, including how many visits a person should make during the antenatal period to be, safe. Is also a systematic review topic. So when you look at a systematic review, what you need to look at and see is, did they ask a question which is relevant to you in terms of the PICO stuff? And were the outcomes, for example, the outcomes they used, was that relevant? So you might find systematic reviews, but the outcomes they're asking are not the kind of outcomes you want to ask. Then you must see whether they really searched for all the databases and not excluded non-English language studies. And what were their criteria for including and excluding studies? And have they documented all the studies that they excluded apart from the ones they included? And what are the ongoing studies and what are the ones that they need translations or something for? So how explicit are they in describing what they found? And how good was their method to assess risk of bias? And how did they extract the data? And did they look at all the things in meta-analysis that we'll be discussing today? And did they finally give you a summary of findings table, which will tell you how confident they are about the results of the systematic review? So I'll go through many of these aspects in a little bit of detail so that you can always go back and look at it to understand what exactly, because it may be too much in one session, but this record is there for you to go back and look at it later on. So the first step is your PICO statement. What's the population that you're looking at? What is the intervention? What the comparison? And what are your outcomes, primary outcomes and secondary outcomes? So once you clarify it like this and your study design, it will help your search, because including important elements of these aspects in your search strategy will help you to find those group of studies which have all the information that you need. And that's the way search strategies are done. And Cochrane searches for trials all over the place. In the Cochrane library, there's a specialized register of studies that each review group has, and looks at other databases like Medline, Embase, which is a European database, and Lilac, which is a Latin American database. We write to the organizations and drug companies if they know of any more trials. And they search the conference proceedings and non-indexed journals to see if they can find additional trials. They write to the authors of trials, they look at the citations, and they look at trials registries. It's a very, very comprehensive search to see which are all the studies that we can include based on their inclusion criteria. So this is a table which is always there in the Cochrane review, which tells you the excluded studies and why they excluded. So it's not an RCT, or the way the drugs were given were not right, so it's not what we want. And then for each included study, they describe it in detail in terms of the methods, the participants, the interventions, the comparisons, and the outcomes. And from each study, they will make an assessment of, was there selection bias, was there detection bias, and it's very explicit. And it gives you the reasons why we think this is high risk bias or low risk of bias. And you can also then get a graphical summary of the bias across the trials and across the domains in each individual trial, which will help you to decide, okay, I had 4 studies in one meta-analysis, and those 4 studies are biased and is likely to influence the outcome. All of these help you when you're looking at how confident you are in the results of these trials. Now coming to this whole concept of meta-analysis per se. It may seem very complicated, but it's not that complicated. It's how you synthesize the data. There are certain principles in meta-analysis. One is, we are looking at meta-analysis providing a weighted average of the effects of one intervention compared to the other. And you need at least 2 studies which have got similar populations, intervals, comparisons, and outcomes to consider pooling the results. If they're very, very dissimilar, then it's better not to pool the results. What you must remember is that we are not comparing patients in one trial with patients in another trial, because they were not randomized that way. We are looking at patients who are randomized within the same study, and the results are analyzed separately for each of those studies. And for each outcome, depending on the number of studies that provide you data for that outcome, you get a forest plot for each outcome. And some outcomes may have more studies giving you data than other outcomes. So suppose you've got 15 studies in a systematic review. Not all of them will give you the outcome for all the outcomes. So depending on the number of studies which are reported that outcome, you take the data from that and pool it. And then you calculate the summary statistic for each study. And those summary statistics are pooled in a meta-analysis with weights added before the pooled result is given. So this pooled weighted average is what meta-analysis does. Now, what do you mean by summary statistic? That is the way you want to represent the results. So for dead alive binary data, you can use a relative risk, or you can use a risk difference, or you can use the odds ratio. If you've got means and standard deviations in continuous data, then you look at the difference in means with their confidence intervals. If you have time to event like survival data, you can use a hazard ratio. So then the question is, how do you weight studies? The principle is this: more weight is given to studies which give us more information. And this usually means it should have more participants, it should have more events, particularly in the control group. That is the baseline risk. I discussed that in part 1. The baseline risk of having that outcome should be fairly high. And then if you have a study which has good relative risks, then the corresponding risk in the other group will basically, it will give you a narrow confidence interval. So this is the three elements which are used to calculate weight, and the weight is inverse of the variance. So the variance here, I think the best way to understand the variance is kind of distribution of the effects, and that's what it uses the standard error, and that's how you calculate your confidence intervals. So I find it simplest to understand by saying a study which has a narrow confidence interval has a lower variance, and that study with a narrow confidence interval will get more weight. If you have a study with a wide confidence interval, then the variance is likely to be high, because the participants are less and the number of events were not very much, so the confidence intervals are wide. And that study will get lower weight. So to keep that in mind, I'm now going to give you an example. We've got 6 studies which looked at the relative risk of death in people who had head injury. So this is controlled hypothermia to slow down the metabolism and prevent death in people who have a head injury. Now, if you look at those 6 studies, it gives you the relative risk and the confidence interval. Now, which study do you think should get the most weight? I'm not sure whether you're attempting to answer this question, but if you look at the first, second, third studies, their confidence intervals are very wide, but the fourth study has got a fairly narrow confidence interval, 0.21 to 0.96. All the other studies have got much wider confidence intervals. So based on that, inverse of the confidence interval width of the is the weight. If you've got a small, narrow confidence interval, it gets more weight. So based on this, you would say that the fourth study should get the most weight. Now, these are the results of individual results of the studies. We had said from the previous slide that the fourth study should get the most weight. But what you will find here is that the fifth study has got a larger sample size. So you might be tempted to think that the fifth study should be given more weight. But what I said is it's not just a question of sample size, but also the baseline risk in the studies. So if you actually look at the weight given to the studies, the fourth study is young, gets the most weight because its baseline risk is much higher than that in Tharyan, and the sample size. So the variance is what really matters. So the important thing to keep in mind is you don't have to calculate all these weights. It's a property of the data, and the software program calculates the weights. You just need to know how it's done. So if you want to look at the formula that's used for calculating these weights, it says here that the weight for a study is events in the control arm into the total of the number in the treatment arm with and without the event, and divided by the total number randomized. So the control group event rate is also important, apart from just the total sample size. Anyway, so in doing a meta-analysis, the steps are, you look at the comparisons. I got drug A versus drug B, and I also want to compare drug C versus drug B, whatever. Then for each of those comparisons, you say, what are the outcomes I'm interested in? So here you can choose death, relapse. And for each of those outcomes, you extract the data from the studies which have reported the data for death, for example. And then you say, okay, I want to look at the relative risk of these studies, and the program will meta-analyze it and give you the relative risk, pooled relative risk with confidence intervals. Then what you're supposed to do and see, are the results consistent across the studies, or is there inconsistency? And if there is inconsistency, can we explain it? And so there are the other steps. And finally, you decide what is the overall summary, right? So looking at, should you combine the data? If you find that the data are so different, studies are also different, you can say, I'm not going to do a meta-analysis. I will just report the results qualitatively, like a narrative. If you find, yes, I have data which is comparable, then depending on whether the data is discrete, like binary data, yes, no, alive, dead, the standard option statistical method is called the second one, Mantel-Haenszel method for pooling data. There are other methods used in different situations, but the common default option is a Mantel-Haenszel, or MH. Okay, and you can pool relative risks and odds ratios and risk differences. So for example, here is thank you. Here is the relative risk and confidence interval for the outcome of neonatal death when steroids are compared with placebo. Sorry. So this is from the systematic review we looked at, and it shows that steroids reduce the risk of death. But this is using the risk ratio Mantel-Hansel method and a fixed effects model. You can change the metric and you can say odds ratio, and it will give you an odds ratio with the confidence intervals from that metric. Now that's how we look at discrete data. And suppose you have continuous data like weight, mean weights and standard deviation for the weight. You've got to look at, do all the trials measure this in the same unit? So if some trials give you weight in kilograms, and the other trial gives you weight in pounds, you'll have to convert it to one common measure. And if you do that, then you just look at the mean difference, the weighted mean difference. And the weights here are based on the width of the standard deviation. You've got a very wide standard deviation, that trial gets less weight. If you've got a very narrow standard deviation, that trial gets more weight. But the problem is, sometimes you'll find trials where they're looking at the same kind of outcome, like say pain, but each trial uses a different pain scale to measure it. Now keep in mind that the pain scales have got different number of items. So if you say the mean on one scale is not the same as the mean on the other scale. So you can't just take the average of all the studies there. You have to find some other way of making it common. That's what you call the standardized mean difference. If you have the unit of measurement across the scales is different, and the studies is different, using different scales, you can pool the data using a method called standardized mean difference. If they're on the same unit, like weight or height or number of days and stuff, you just have to just pool the difference and look at the mean difference. So this is the mean difference in studies comparing antibiotics, mean number of days of cough. So in these studies, what they've done is they extract the mean and standard deviation from each of the studies and the number of people in that arm, and they calculate the mean difference from each study. And when they pool it, they weight it according to the standard deviation. If you look at the second study, the fourth, one, two, three, the first study that gets the most weight because it's got a standard deviation of 2 and 3. All the other studies have got overall the standard deviations are more. Now the problem is, how do you interpret mean difference of minus 0.58? So because here this number of days of cough, minus 0.58 means less than 1 day, but half a day less. So the problem with whenever you look at continuous data is to make a decision, is it really clinically important, right? So you might need to find from other sources whether half a day of cough is important for patients. Probably not. When you're looking at standardized mean difference, what you're doing is you're looking at the mean outcome between the groups and dividing it by the standard deviation of the outcome. So what you then convert your results is into units of standard deviation. It's a slightly more complicated way of trying to interpret the data, but that's what you can do. So I want you to be able to interpret a forest plot. And I'm showing you a forest plot of a comparison of 2 anti-obesity drugs, and the outcome is death. Now what you have here is the study ID and the year of publication of these trials. And you have 1, 2, 3, 4, 5 studies done between 1999 and 2010. And from each of the studies, the number of people who died given drug A and the number of people who died given drug B are extracted. And you will find that totally 51 people given drug A out of the 930 given drug A died, and 72 out of the 928 given drug B died. We are not going to take the average of these studies, that is 51 divided by 930 compared to 72 divided by 928. That's not what we're doing, because there you're breaking the power of randomization. What we're doing is, for each study, the relative risk and confidence intervals are calculated. and there are no weights attached. So if you calculate the relative risk and confidence intervals, you will get the same results. Here, we are showing the graphical display where if the confidence interval goes across to the other side, then it shows that we are not sure whether it works or doesn't work, and it's statistically not significant. If it doesn't cross the other side, to the other side, then it's a result favoring or not favoring the drug. And the blob in the center represents the weight given to the study. So if you look at this forest plot, the 1, 2, 3, 4, fifth study has got the largest blob, and that corresponds to the weight given to the study. So I got 60% of the weight in the pooled meta-analysis, and that's because its confidence intervals was the most narrow. You'll also see it got a very large sample size, but it's not only sample size that matters, it's the width of the confidence interval. For example, if you look at the study which has got the next largest sample size, it's the third one, Jesani, with 85 and 85 in each arm. But it got the least weight, 6.9%. So it's not just sample size, it's also the control group event rate. 5 out of 85 is not much of a baseline risk. But more importantly, look at the width of the confidence interval, 2.27 to 13.81. So it's got a very wide confidence interval and got the least weight. So this is how a forest plot looks like. And that's the pool effect estimate. It's an estimate, it says 0.70. So here the outcome is death. So anything less than 1 means drug A is better than drug B. And 0.70 means that drug A reduces the risk of death by 30%. And how sure are we of that? Your confidence interval is 0.50 to 0.99. So a 0.50 means a 50% reduction in the risk of death. That's your best estimate. A 0.99 means a 1% reduction in the risk of death. That's your least estimate. Now, because the confidence intervals do not cross 1, you would say this is statistically significant. You can make out that's the overall effect. The p-value is 0.04. If it touches 1, then the p-value will be 0.05. But while it is statistically significant, the question is it clinically important? And like we said before, the estimate is a 30% reduction, which is clinically important, but the least estimate is only a 1% reduction. So we're not very sure that this is going to be clinically important in the real world. When your least estimate is only a 1%, it's statistically significant, but it's not clinically, we're not sure whether it's clinically important. As I said, this is how you do. You pool the estimates, weighting it, and then you look at the clinical effect, the likelihood that's going to be clinically effective. The next step is to see how consistent are the results. So we need to look and say, we need to understand when do you expect inconsistent results in the trials, and how can we say that this difference in the results is not due to chance? Any difference can be a chance difference. How do we say this is not a chance difference? And then if we say it's not a chance difference, how much of it is more than chance and how much of it is chance? These are the three things we can go through right now. So when do you expect to find inconsistent results or heterogeneous results? If the trials had differing kind of populations, like older people, younger people, if the interventions and comparisons were different, like some used higher doses or lower doses, or gave it early, gave it late, gave it IV, gave it, whatever way, then you can get differences. Or when the outcomes are measured in different ways, some people measure it using a different definition, some people measure it with another definition, or they measure it at different time points, some measure it 2 months, some measure it 2 years, you can expect the results to be different. And when the trials are done differently, some people randomized properly, some did not, the results will change. And sometimes the variation in results could be just due to chance across the studies. So it matters, heterogeneity matters, because we are saying this is an average effect. Now, if you're saying it's an average effect, there can't be many outliers, right? To say this is the average. all the studies should be more or less the same. Then you can say this average represents the results of all the studies. If you find the studies are differing quite a lot, it basically means in some studies the intervention is working better or it's not working so well if it goes the other direction. And just ignoring that is not a useful strategy. So what we can do to identify heterogeneity is that we can look at the confidence intervals and see do they overlap. If they do not overlap, then it suggests that there is heterogeneity. So what I mean here is looking at this forest plot. The first study, George 1999, made a prediction. It predicted that the effect estimate will lie somewhere between 0.07 to 1.37. That's a prediction from this trial's estimate that this is what I expect you to get. The next trial, Thomas 2002, fulfilled that prediction. It fell within that prediction limit, but extended a little bit. So now the new prediction is 0.07 to 1.3 to 1.75. So if you look at the other trials in the series, Srinivasan and Pai, they also fulfill this prediction. But Jasani is an outlier. It does not fulfill this prediction. The least estimate is 1.75, and the best estimate in Jasani is 2.27. There is no overlap there. So that clearly tells you the results are inconsistent. The next thing we can do, we have to ask is how do we know this is not due to chance? Right. So there's a chi-square test for heterogeneity. And here, because we know that if you have a very small sample size, the chi-square test is not very powerful in picking up differences. So here we use a p-value of less than 0.1, not 0.5, to say a 90%, we'll say at this level, we'll say it could be heterogeneity. It's not more than due to chance. And then there's another statistic you can calculate from the chi-square called the I-square, inconsistency. And it tells you how much of the difference is not due to chance. So if you say you've got an I-square of 25%, that means 75% of this variation in the results is due to chance. Only 25% is not due to chance. When you get up to 75% I-square, you're saying that only 25% of the variation is chance, 75% is not chance. It's a true difference in the results of the studies. So then you can't ignore it. So looking back at this forest plot, what do you see? You see that the eyeball test tells you that Jasani is clearly an outlier. And the chi-square test tells you the p-value for the chi-square test is less than 0.00001. So what it tells you is that you're more than 99.99999% sure that the difference in the results of these trials is not due to chance. Right? It's a true difference. And the I-square of 87% tells you that 87% of the difference in the results of these trials exceeds chance, is not due to chance. Only 13% is due to chance. So this is clearly a very heterogeneous result, in which case the pooled estimate of 0.70, 0.5 to 0.9 is not a true estimate of the results of the studies. It assumes that the difference in all the, what you've done is we use a fixed effects model. What the fixed effects model is assuming is that that pooled estimate and all the estimates in all the studies actually should be in a straight line. It should be exactly the same. And the difference why they're not the same is due to chance differences. That is, within the study there is a variance. That is, the confidence interval represents the within study variance of the trial, right? But the reason why the effect estimates, the blue blobs, are not exactly in the same line is a chance difference. That's the fixed effects model. And you prove the fixed effects model by showing that your p-value is more than 0.1, and that your I-square is less than 25%. And you're saying most of the difference is just chance. Actually, the two differences is the same. That's the fixed effects model. But here what we've shown, you cannot assume that this is a fixed effects model because your p-value says that, no, this difference is not just a chance difference. The reason why those effect estimates are not all that are not in the same line all over the place is due to something different in the trials. Only 13% of the difference can be accounted for by chance. So this is the problem here. So when you detect heterogeneity, that is, if your confidence don't overlap and your p-value is less than 0.1, if your I-square is 25% or less, it says that 75% or more of this variation is just chance. Continue with the fixed effects model. Assume the drug works the same in all these trials, and these minor differences are not very important, right? Suppose you find that your I-square is 75% or more, then you can do the next option, which is don't prove. You can't explain it, just don't prove it, right? But if you find that your confidence intervals, where I-square is 50% or more, somewhere in between, 25% and 75%, then you say, I might be able to explain this difference if I can find why are the trials different. So basically a subgroup analysis might help you explain the heterogeneity in the trials, right? You can also use meta-regression. That's a more complicated technique, and you need to have many, many more studies for you to do a proper meta-regression. Or if you can get the individual patient data from each of the studies, then you can look at why the study is different. But that's usually not easy to do. So a subgroup analysis is fairly simple to do. And what we're looking for is in the trials in the meta-analysis, right? What are the differences in the characteristics of the inclusion, exclusion criteria, etc., which might be associated with the difference in the treatment effects? For example, allocation concealment, age group of patients, setting of the study, dose of drug. Could they explain why the studies are different, why the results are different? So I'm going to give you an example from this study where you find there are outliers and the rest of the studies seem the same. So if you went and looked at the studies and found that the 4 studies which clearly favor the intervention and where the I-square is 0%, so there's no difference in the results of the trials, right? What you're basically finding that the reason, when I-square is 0%, it says nothing exceeds, there is no variation in why the results are not exactly in the same line is just chance. The p-value is 0.58. You're not ruled out the effects of chance. Otherwise, actually, all the studies should have an estimate of 0.34. But because the confidence intervals all overlap, it's basically saying it could be anywhere between here and here. So you can be fairly certain that this results are consistently showing that drug A is better than drug B. Now, what is the difference in this group of studies? None of them included patients who had bad cardiac risk. None of them had angina or myocardial infarction. They were not on any cardiac drugs. And in this subgroup of patients, drug A is better than drug B for the outcome of death. Jesani did not exclude people with cardiac risk factors. And so his study, his patients had more people who died on drug A. So we are not giving you the pooled effect estimate for both. We're just telling you, in the subgroup, with four trials where people did not have cardiac risk factors, drug A is better than drug B consistently. We are not very sure about Jesani's results because it's only one study, but it seems to indicate that if you've got cardiac risk factors, drug B is better than drug B. So that's how we've explained the heterogeneity in the meta-analysis. Now, the final way you can do is you can't explain the heterogeneity. You've got a lot of variation in results. Then you change the way you think about the whole thing. You don't say the drug works in a fixed way and that the inconsistency is only random error, but you're going to say the each trial seems to have a different effect. And the overall differences in the studies is not just random error, but also true differences in the trial. So you're saying we can't assume that the drug is working the same way because our p-values and our I-square tells us there is certainly more than just chance playing here, right? So here we are just giving you a pooled result is only the mean of the range of effects from a random distribution. It's a very vague or other imprecise way of pooling the results, random effects. Yeah. So what you're saying is that it allows for two sources of variation. That is chance plus true differences in the studies. So then the weights given are quite different, because I'll explain why the weights are different in a random effects model. And because when you give more equal weights, you find that the confidence interval becomes wider. So this is what I mean. So if you look at the left, the fixed effect weight comes, it's inverse of the variance within the study. That means your confidence interval, that is your variance, right? And the variance in this, that is the only source of weight. So if you've got a study with a very narrow confidence interval, because it's got a large sample size and more events, then that study will get more weight, inversely, right? And if you find a study with a wider confidence interval, that gets less weight. So there's only one source of variation. Okay, but if you look at the random effects model, it's got two sources of variation. One is the within study variation, which is the width of the confidence interval, and the other is the between study variation, which is the difference in the estimates and the confidence interval within the studies themselves. Okay, so when you have two sources of variation, the weights will become increasingly different, right? And when the between study variation is large enough, that becomes a dominant source. So then what happens is that the weights get smaller and smaller and smaller, the more the between study variation becomes. So it's like saying that the true effect, there is no one true effect. Each study has got its own true effect. And what we are describing in a random effects model is the mean of the distribution of the effects. And there's a term called tau, which is actually the standard deviation of this particular distribution. So it kind of assumes that there is the difference y is accounted for by random error plus true difference from the mean of the effects of the three studies. Anyway, what it tells you is that if you find your I-square is pretty high, more than 25%, increasingly it shows there are some differences in the studies which you've not been able to explain by a subgroup analysis, and therefore you have to be careful when you pool the results. You can't assume that every study is working the same way. You've got to give more weight to each of the studies individually, not only the studies with the small confidence interval. So an example I can show you is a systematic review from the Cochrane Library, which looked at azithromycin versus amoxicillin for treating acute lower respiratory tract infection, and the outcome here is clinical failure. So if you look at the top forest plot, they've used odds ratios and a fixed effects model. And it kind of shows that the odds is about 0.67 lower with azithromycin compared to amoxicillin for clinical failure. And the confidence interval ranges from 0.46 to 0.96. 0.96 is not a significantly different odds, but it is statistically significant because it doesn't include one. The overall effect estimate shows a p-value is 0.03. Okay, but the problem is that your I-squared is 82%. Shows that only 18% of this difference in the results is due to random error or chance. It shows that 82% of it is due to something different in the studies themselves. And what you then normally do is try and see, can I explain this by subgroup analysis? But if you can't find any biologically plausible reason to explain any differences here, you're stuck with that result. So then instead of saying that I'm telling you the drug works in the same way in all the studies, I like to acknowledge that the drug works differently in all the studies and I don't know why they're doing it. I'm going to use a random effects model. So in the random effects model, what happens is that the results tend to be much more conservative. It doesn't affect the heterogeneity. Studies are heterogeneous, but it determines how you're going to interpret the pool results. Because here, when you use a random effects model, the confidence interval becomes much wider. That happens because in the random effects model, the weights are distributed more evenly, and it depends on what the intertrial variability is, apart from the confidence interval of the individual studies. What is the difference in the confidence interval between one study and the other? those two sources of variation then will give you narrow, wider confidence interval, because you take a look at the second study. In the fixed effects model, that second study got only 5.89% of the weight. In the random effects model, it gets 17% of the weight. So it pulls the results towards it. Whereas in the earlier analysis, it was not influencing the overall results. Now it is influencing the results, and it becomes a more conservative estimate of what the overall effect is. So that's the difference between the fixed and the random effects model. The fixed effects model estimates the average effect across the studies and assumes that the intervention has a fixed effect in all the studies, and any variation is due to random error or chance, right? So it gives more weight to studies with lower variance or narrower confidence intervals. The random effects model is not giving you the average effect, it's giving you the mean of the distribution of the effects, and it assumes that each study has its own effect. And the variations in the results are not just chance, but also some difference in the effects of the interventions. So the weights are given more evenly to account for both these sources of variation. Right. So once you've done the systematic review and you've got your forest plot, now the job is to summarize the results so that other people can understand what this means. So in order to evaluate the effects of a systematic review, we need to know a few things. One is, how good are the results? Are they going to be clinically important for all the effect measure outcomes we are interested in, like efficacy and safety? We're not only looking for statistically significant, but is there a substantial benefit that could be clinically useful? Second is, we want to know, how do we know that these results will be what you get in practice? And how do we know that doing more research is not going to change these estimates? Okay, that's really what we want. So in the grade approach to summarizing the findings of a systematic review, what we do is we create a summary of findings table for each comparison. Suppose you've got only one comparison, one summary of findings table, drug A versus drug B. But if you've got more than one, then you will have each comparison has a separate summary of findings table. Then you choose the maximum 7 critically important outcomes that will help clinical decisions or policy decisions. So these are likely to be clinical outcomes, not blood tests or proxy outcomes, because they are not the direct clinical outcome they're looking at. They're only intermediary outcomes. And for each of those outcomes, we provide you the absolute benefit, the relative effects, the number of studies that gave you this information, and finally, a confidence assessment about this result. Okay. So to get this confidence assessment, let's take the outcome of death between steroids versus non-steroids. We look to see how many studies contributed to this meta-analysis. And we presume that any systematic review of randomized controlled trials is going to be good quality. So it starts as high quality evidence, high confidence evidence. But if we find that a few of the studies in that outcome for death were badly flawed, we can't trust those results, then it will affect our confidence in the overall study result. It's a limitation, and it will reduce our confidence in that overall effect. Then we want to know is, can we apply this result directly to our settings, which means that we need to know who were included in the studies and who were excluded in terms of populations, comparisons, outcomes, health system. We see, are these comparable to my city? And if they are, we are confident in the results. But if for some reason we feel that this study population or interventions did not really match what I'm interested in, then our confidence that this result is going to apply to me comes down. Okay? So, for example, in a review which was done, looking at antibiotics for Shigella dysentery, right? Most of the studies had excluded people with children with severe malnutrition. And that's because ethics committees won't allow you to randomize children with severe malnutrition in any trial. But the problem in the real world is lots of children with severe malnutrition get dysentery and they may die. So the results of those trials are not really directly applicable to us because some of it is missing, the information we want is missing. And that will reduce our confidence in the results of that systematic review of those trials. Okay, so that's an example of how the directness is compromised and your confidence in the review comes down. And the next thing you want to know is, are all the results consistent, as we just discussed? And if they are inconsistent, can you explain it adequately in a subgroup analysis? Because if you can explain it, then you don't have to worry. You know why. But if you cannot explain it and you're using a random effects model to prove the results, then our confidence in the results comes down. Okay? And the next question is, are the results precise? Now, what I mean by precision here is, you've got two ends of a confidence interval which give you the best estimate and worst estimate of the effects of that intervention. Now, if you have to ask yourself this question, if the actual result was the best estimate, would I use the result? Would I actually say, yes, I want to use it, or I won't use it? And if I look at the least estimate, will I have the same decision or will I change my decision? If you have the same decision, whether it's the upper or the lower limit of the confidence interval, that result is precise. If you have a decision which is different, depending on whether it's the upper or lower end, and that result is not precise, and your confidence in the overall result comes down, right? Also, you want to ask yourself, did they study enough people and have enough events to say that you have enough data to say it works? If that also is not very good, then you will say the data is imprecise and your confidence comes down. The final thing is, are you sure you've got all the evidence, or do you have some indication there could be some studies which you've not been able to access? If you have got all the evidence, then you're confident that this overall result is, you're certain of the evidence. So what happens is that in the review, for each critically important or important outcome, you create a summary of findings table based on the results of the meta-analysis. And basically the programs help you to do all this, but you have to make a decision about how confident you are the results are. Based on, for RCTs, they consider high quality evidence, but if there are risk of bias, inconsistency, indirectness, imprecision, or publication bias, you might downgrade the evidence. So the factors that decrease our confidence in the certainty of evidence from RCTs and bring it down from high certainty by either one level or two levels are these factors which we just discussed. Then the other thing is that in observational studies, they consider to be low quality because there is potential selection bias. And they may be even badly done, in which case you have very little confidence in their results. But if they are well done, you can even consider increasing your confidence in the results by upgrading it, because the study result shows, really powerful effects. So even if it is from an observational study, it's not going to completely change the opposite way. So if you get risk reduction of something like 90% with some intervention from observational studies, which are done well, in the real world, it's not going to become zero. So you say, I'm confident that this is a good result, even though there are observational studies. The other thing you might say is that, okay, these studies are done very well, but there were some confounders in some of those studies, and if those confounders were not there, the results would have been even better. That could be another reason why you say I have more confidence in results. And finally, you will find that across a body of observational studies, like cohort studies, assessing the relationship between, say, warfarin and bleeding, right? That with increasing dose across the studies, there is increasing risk of bleeding. That again gives you confidence that these observational studies are showing you that higher doses are associated with more bleeding risk. Anyway, it summarizes the way we confidently say. So what then happens is that we end up with 4 levels of certainty. High certainty means we are very confident that this result for this outcome is likely to be a true estimate, and you don't need to do any more research. It's going to change the estimate. When you have moderate confidence in the result estimate, you're saying that the true effect is probably likely to be this, but because of this one reason, heterogeneity or imprecision, our confidence is lower by one level. Then it comes down to moderate. When you say you've got low certainty evidence, you're saying it may give you this result, but because of these two reasons, right? We think that this may not be the true estimate and we might need to do more research. And when you get very low quality evidence, it basically says we don't know what the result actually is. We certainly will need to do more research because of these variations, these problems in the overall study. Okay, now this is then used by a group of people who then make a decision of should we use or should we not use the evidence. And it's based on it's a panel of stakeholders who look at the balance of benefits, harms, costs, burdens, and preferences and make a decision saying a strong recommendation to use this intervention based on high quality evidence or on moderate quality evidence, or a conditional recommendation to use this intervention based on high, moderate. Most probably you will not get a recommendation based on to use something based on low, very low quality evidence. Okay, so I'd like to give you a real world example of how this works. This is from India. And this is based, there was this girl called Gauri Kalapati who in 2002 asked this question, why is it that in India, Sri Lanka and in Pakistan, when you want to treat bivax malaria and prevent relapses, we use 5 days of primaquine, whereas WHO says you should use 14 days of primaquine to eradicate the echinocytes after you use chloroquine to kill the blood forms. So she got into this partnership with the Cochrane Group. We were part of this effort, and we asked this in the form of a systematic review question, which was published. Primaquine for preventing relapse in people with Plasmodium vivax malaria treated with chloroquine. And in which one of the comparisons we were looking at is 5 days versus 14 days of primaquine. And this is the result from a forest plot of trials. There were 3 trials which looked at primaquine 5 days plus chloroquine compared to chloroquine alone to see whether you need primaquine. And the outcome was parasitemia, relapse after 30 days, which showed basically that if you give 5 days of primaquine following chloroquine or don't give primaquine at all following chloroquine, the relapse rates are the same. And that is what our countries were doing, giving 5 days of primaquine after chloroquine. Other studies, 1, 2, 3, 4, 5 studies show that if you give 14 days of primaquine after chloroquine, compared to chloroquine alone, 14 days of primaquine plus chloroquine is far superior to chloroquine alone, right? And then when you look at the direct comparison of 5 versus 14 days of primaquine from 2 studies, here again 14 days of primaquine clearly superior to 5 days of primaquine. So this study showed from direct as well as indirect evidence of trials that our policy of giving 5 days of primaquine was inferior to giving 14 days of primaquine and probably as good as giving nothing. So this is a summary of findings table from the main comparison of 5 versus 14 days. And this summary is meant to be useful for people to make a clear impression of what the entire review was trying to do. So it tells you when you use 5 days versus 14 days of primaquine after chloroquine, looking at the outcome of relapse over a period of 3 to 6 months follow-up. If you use primaquine 14 days, you can assume that you will get about 21 relapses per 1,000. And if you use 5 days of primaquine, like we are all doing, you can expect to get 183 more relapses per 1,000, from 49 more to 742 more. And this assumption comes from a relative risk from the meta-analysis, which you just saw, a relative risk of 10.05, 2.82 to 35.86. I'll show you what I mean. This is the PO study. So what happens then is that we have to make quality assessment of grade assessment. And the grade assessment is moderate. Right. Now, moderate means that it's not high certainty. For some reason, we have downgraded our confidence. So we have to see what the footnotes tell us. And the footnotes tell us that there were no serious study limitations, there was no serious inconsistency, but there was serious indirectness because they didn't have enough children. They didn't include children in these trials, and the trials came from low transmission areas. So because of this, we felt that it's not complete in terms of the evidence base, and we downgraded by 1. But otherwise, it basically means that this is a good estimate. What is very interesting was that we were able to actually change policy by going to the ICMR and presenting this review to them, and also giving them a 1-page summary of the evidence, and they helped us to change the malaria drug policy because it changed. The review was published in 2007, and the policy changed in 2000 in a few months. 14 days is now what we give. Moreover, we found that the Park and Parks textbook of preventive and social medicine had changed the recommendation to 14 days in 2000. So systematic reviews can actually make a difference. I want to conclude this by talking about the Cochrane Library and reminding you that the Cochrane Library evidence is of the people, by the people, and should be for all people. And I'm going to give you this example. This is a blog written by a guy called Bart Knowles, who writes about malaria. And in this blog post, he talked about a flight he took from Copenhagen to Amsterdam for a workshop on malaria and stuff. And he was reading an article, and it said that the mosquito is the in-flight magazine article, most dangerous animal in the world because it kills so many people. But then when he looked at the advertisements, he found in that glossy magazine, he found an advertisement for electronic mosquito repellent called Mosstop, based on the Akita brand Mosstop. Apparently it does some kind of supersonic noise and kills mosquitoes. So he was very skeptical about this, and so when he went back home, he found a Cochrane review on electronic mosquito repellents for preventing mosquito bites and malaria infection, where the authors had done entomology studies. So you can't randomize mosquitoes. So what they do is you go into the field and they do studies on mosquitoes with the device and without the device, and found it has no effect in preventing mosquito bites. So they felt that there was no justification for marketing them to prevent malaria infection. Based with this evidence, he wrote to the airlines. And he told them that we are actually selling something which is ineffective to people who might be going to places where they could get malaria. And that's unethical because they're not then actually buying stuff which could prevent malaria. Interestingly enough, Singapore Airlines, British Airways, and KLM, all three of them were marketing it. All three of them stopped marketing it based on the evidence of ineffectiveness from this citizen of the world. So what I'd like to actually tell you is in this two-part series that I talked about, I've been emphasizing over and over again that good research is meant to improve patient outcomes, not to improve your own personal portfolio of stuff. And for good evidence, you need collaborative. It's not a competitive approach. So here, this gentleman here is Ian Chalmers, and he is the person who founded the Cochrane collaboration. And he was given a knighthood. He became Sir Ian Chalmers in 2005 or so. And when you become a knight of the Royal Empire, the British Empire, you are given the opportunity to have your portrait painted and hanging in the National Portrait Gallery in the UK, in London. So he asked all of us who were part of the collaboration to say, hey, can you give me a picture? Because I'm going to retire shortly and I want to remember all of it. So all of us sent our pictures to him. And this is the portrait of Ian Chalmers hanging in the National Portrait Gallery with all our pictures there. Because he said very clearly, this entire effort is a collaborative effort. So I want you to leave you with this thought that, whatever research that you do or try to do, or it's collaboration that matters. That's what gives you good health outcomes. So I want to thank you for your patient listening. And if you have any questions, you can email me. My email address is prathap@gmail.com. Thank you. Do you have any questions at this point in time? Or would you like to email me later? Okay. Stop sharing.
Yes.